Yeah. Right. So what we're going to talk about today is about designing data warehouses in BigQuery and why it's different from the way we used to design data warehouses like 20 years ago. And, and especially what I want to focus on is what is it about BigQuery that makes it so different, that makes it high performant and makes it very fast and makes it very efficient, but it also requires us to change a little bit about how we think about how we design data warehouses. So first thing, I just want to point out that this is an architecture discussion, so there won't be a lot of visuals of screenshots from the BigQuery interface or command lines, with details about how to execute a particular operation. Instead, it's more about how is BigQuery put together, like what are its components that influence how we make decisions about how we design our data model. So just at a high level, I just want to point out there are three broad areas of Datastore Options. The first is relational, and those are databases that have been around the longest. They're highly structured. We often use them for transaction processing systems. While they work really well in many cases, they can be difficult to scale. Now, NoSQL databases emerged in the last couple of decades in response to that difficulty around scaling relational databases. And NoSQL works really well with semi-structured data, especially in applications where when you're replicating data, the replicated data doesn't have to be immediately consistent. And then also the third type is an analytical database. And that's really designed for structure database like relational, but it's also designed to be highly scalable. And what we give up is some of the transactional capabilities. And BigQuery is an analytical database. And so what we're going to do is dig into a little bit about how that's different from what has typically been the case with data warehouses. So early on, so sort of like the early data warehouses were typically designed for relational databases, and we had usually one server, maybe a small cluster like an Oracle cluster. But the key thing was that the storage and the compute resources were tightly coupled. So if you wanted to scale up storage, you were also scaling up your compute resources and vice versa. Typically, when the data warehouse got too big or performance got too slow, we would have to scale vertically, which means we just need a bigger server, more memory, more disk space. And also, these data warehouses, we typically use the same software we use for OLTP systems. So, we might be using Oracle for an online transaction processing system, and we might use the same version of the software to build a data warehouse. And we might change some configurations. We might change block sizes and things like that to have larger block sizes in the data warehouse. But essentially, we're working with the same engine. So it wasn't really optimized for analytical operations. We were taking a tool that was optimized for OLTP and using it for analytical operations. Now, BigQuery is different now in the sense that it's a serverless data warehouse designed right from the beginning to be petabyte scale. So immediately right out of the box, we can start to begin to understand why BigQuery had to be designed differently. Now, BigQuery does use SQL, but it's not a relational database. It's an analytical database. So that means it's really designed for these analytic workloads that are sort of read intensive and don't require transaction processing. Now, there's some other features of BigQuery that are really interesting and make it really appealing. I won't get into these today, but I just want to point them out. BigQuery has BigQuery ML, which allows you to do machine learning directly in BigQuery. You don't have to export the data or go use Python or Spark or anything. You can work with your data right in the database and use SQL commands to implement machine learning. BigQuery now has a BI engine, which is like essentially an in-memory OLAP queue, which makes you allows you to do very low latency operations on large amounts of data. And there's BigQuery GIS if you are interested in geographical systems. Okay, so really under the hood, what's so different about BigQuery? Well, it all comes down to the architecture. And this is probably one of my favorite images that Google has provided about BigQuery. I think it really succinctly captures what's going on here. the key takeaway here is like over on the left, we have our storage system, and over on the right, we have our compute system. And they really are two separate things. In fact, these were developed separately. There's Colossus, which is the successor of the Google file system. This is the global data store, like block storage, data storage system that Google uses. And it's used by multiple systems. Bigtable uses it, Spanner uses it. So Colossus is essentially, if you want to write data to a highly reliable persistent storage, it goes to Colossus. Now, typically we think, oh, well, that sounds like network attack storage. You're going to get really long latencies if we're going from a server over the network to grab data. But Google solved that problem by creating these proprietary networking switches that they call Jupiter. It's the Jupiter project, or Jupiter switches. And it's a petabit network. So it has very high throughput. And that means that basically you can go across the network and get the same kind of latencies you would typically get from a server that you might have on-prem that has a direct attached storage. Now, on the compute side, there's really two important components. There's Dremel, and Dremel is a software system which manages a cluster of servers and is responsible for executing SQL queries. So Dremel's really the thing that creates a job that is then executed and managed by Borg. And Borg is the predecessor of Kubernetes, so it's like a job scheduler, and it manages the resources. Now, because BigQuery is multi-tenant, you and I and a bunch of other people all want access to the same resources. Borg and Dremel manage those. Borg manages sort of the SQL jobs, and then there's also the process of managing some of the resources so that they're fairly allocated. And that's something that comes with Dremel. So let's look at each of these components and kind of dig down a little bit, because they all really influence why we do things in BigQuery the way we do. So again, as I said, Dremel's a multi-tenant cluster. So there's no isolating, large volume customers in one physical cluster and others. No, we're all in the same multi-tenant BigQuery pool of resources. Now, Dremel, as I mentioned, maps SQL queries into execution trees. And execution trees is just a name for splitting up a SQL query into a bunch of jobs that can then be executed in a way that produces the required results. Now, these trees, of course, have leaves, and the leaves of the execution trees are called slots. And slots are the compute resources that read data and perform basic computation. So you can think of slots as like a processor and some memory, but basically it's a computation unit that can do the work and has network access and things like that. Now, the inner nodes in the tree perform aggregation. So as you're doing some low-level processing, say you're grabbing a bunch of rows, you're selecting, you're grabbing a bunch of data across multiple rows. You might pick, say, a particular column, and you might need to transform that column or do a calculation on it. That kind of thing is done at the slot level, at the leaf node. Then if you need to aggregate that and, say, combine it with the results that other slots are producing, that work is performed in the inner nodes. Dremel can dynamically allocate slots to queries. And so that's why you can allow fairness, or basically, you don't have the kind of effects you might see like in virtual machines where you have multiple hosts, multiple VMs, and you have the noisy neighbor problem where you might have, one machine trying to consume too much. So Dremel is designed right from the beginning to maintain fairness. Now, that doesn't mean everybody gets the same number of slots. It all depends based on what's available and what's required. Single users can get many slots if that's what they need, but then get few slots if few slots will do the job. But here's another visualization that shows sort of a drill down into the Dremel Borg architecture. And what you'll notice at the bottom is we have Colossus. And again, Colossus is the global file system and data storage system. And it depends on the Jupyter network and the Jupyter switches to move data between Dremel and Colossus. Now, within Dremel, we have the leaf nodes at the bottom, so those are the slots that do the computation. And when we're moving data between, say, the leaf nodes and the mixers, those inner nodes, and the root server, and the root server is the thing that basically builds the query plan, the SQL plan, the execution tree. When moving data between those nodes, we're also depending on Jupyter as well. So we have very low latency between all of the servers, regardless of what kind of work they're doing. And then around Dremel, you'll notice over to the left, we mentioned the Borg. And again, Borg is sort of is basically like a job scheduler at this point, and it's trying to figure out how to make sure all of these nodes are being used efficiently. Now, Colossus, as I mentioned, is a distributed storage system. And this is really handy because basically it manages so many sort of storage management functions, things like replication and recovery. We don't need to worry about failover servers and hot standbys and things like that used to like take up a lot of mental energy and a lot of DBA time to kind of figure out. And also, we don't even need to think about storage systems. You know, when I used to work on like Oracle and stuff, we constantly thinking of, you know, what do we have available? What's our growth rate? What do we think we're going to need? How soon do we need to order disks so that we have enough? We don't need to deal with any of that stuff anymore. It's basically, we just assume that there's enough storage out there for our petabyte scale database. Now, Jupyter, again, global networking switch, and it's petabit scale. That's the critical thing. And it's both for storage to compute communication, but also compute to compute. And one of the nice things about this is that Google, like Google BigQuery, doesn't need to have rack awareness. And what that means is if you've worked with other distributed computing systems like Spark, you might have come across this idea that jobs try to be scheduled, or the scheduler will try and schedule jobs in a way so that as the job is broken down and distributed across multiple servers, those servers are all in the same rack, because within rack communication is much faster than going from between racks. But in the case with the Jupyter network, it doesn't make any difference where it is. You still have petabit scale networking between them, so you have low latency. So you don't have to kind of have that extra overhead of trying to think about rack-based efficiency optimizations, because it's just not needed. And then Borg, again, really the key thing about Borg was it the predecessor of Kubernetes, and it just manages the mixers and the slots. Now, another component that wasn't in the diagram, but I think is just as important, is Capacitor. And that's a column storage format. It's not part of the architecture, but it's the way we use the architecture. And it's designed to support semi-structured data. Now, the critical things about Capacitor is that it's built from the ground up to support nested structures. So you can think, if you're thinking of terms of like JSON or hierarchies, it's designed right off the bat to support that. And it can also support arrays or repeated fields. And as an optimization, if you're thinking, oh, nested structures, you have to like maintain the whole nested tree and be able to walk down the tree to get to a particular node, say deep in the hierarchy. That's not the case with Capacitor. It's optimized. It has certain levels, metadata that tracks about every row, so that it's very efficient to get to attributes that are lower down in the nested structure. So there's no need to read the entire parent column to produce a nested structure attribute. And Capacitor also has specialized compression that make it very efficient to store data. And Capacitors, again, it's a columnar storage format, which works really well with analytical databases, because typically we might have very wide tables. We have a lot of columns, but when we query, we're often picking a small subset of those queries. So it's very efficient to say, get all of the columns from many rows versus getting all the columns from a few rows. So Capacitor is really designed specifically for this kind of analytical application. All right, so this is all well and good. So now we have a sort of a peek under the hood of what's going on in the Google data centers. But what does this mean for us when we're building data model. So I would just say, I'll go to the punchline right now, and I'll sort of give it all right now, and then we'll drill into the details. So first thing to remember, so this is a distributed system, so things are happening in parallel. And the things, at the end of the day, databases are very good at scanning data blocks, looking for pieces of data. And BigQuery is like that as well. In fact, it's so good at scanning that it doesn't even have indexes. Right, so there are no indexes, which is a sort of a staple of data warehousing when you're using a relational database management system. So what we want to remember is everything we're doing from a design perspective, is driven by the knowledge that BigQuery is basically a big scanner, and it's scanning through our data. Oh, and the other thing to keep in mind is that Google charges for BigQuery based on how much data you scan. So Google has a vested interest in all of us being very efficient and using the Google resources efficiently, and they incentivize us to do that as well by charging for how much data we scan. Also, so then the question is, well, how do we reduce the amount of data we scan? Well, partitioning is a big one. Partitioning basically breaks up big tables into smaller tables, and it allows us to minimize the amount of data we're scanning to answer a particular query. Now, BigQuery has something known as clustered tables or clustered partitions. And basically, that's another way of reducing scanning. And the way we reduce scanning is by keeping the data in some kind of order within that partition. So we can take advantage of the fact that the partition is always kept in sort order. Now, BigQuery supports joins, and it's not a problem to do joins, but it can require shuffling across slots. So another thing that we can do that can make things a little more efficient is to actually denormalize and take advantage of Capacitor by using nested and repeated fields. So these are sort of the data modeling techniques that go against the grain of many things that you might have practiced when designing for OLTP, or even for denormalized data warehouses when using a relational database management system. But these are sort of best practices, good patterns to use when designing for BigQuery, because BigQuery is built differently from other databases. So we don't want to carry over practices and patterns that we use that were sort of optimized for one type of system in one architecture and bring it over to another architecture where it's not a great fit. So the idea behind partitioning, as I mentioned, is just making a big table feel smaller. And here we have 5 partitions. Now, those partitions all have like some range of values that they take care of. So partition A might be, 1 to 100. Excuse me. Partition B might be 100 to 200 and so on. Excuse me. And so with partitioning, we're able to specify in our where clause, oh, I'm looking for range, 310 to 320. Well, then we know immediately we only need to scan partition C. And if it's clustered, if it's ordered, we can even reduce it further. But the idea here is, again, we're just basically breaking up a big table into ordered chunks, and we know what the order is, and we can use that to optimize our queries. Now, so again, partition tables are just tables that are grouped into partitions, and it improves query performance because we're reducing the amount of data that's scanned. Now, there are a few different ways to partition a table. We can partition by ingestion time. And so what happens is, as we're loading data in, it's loaded into a daily date-based partition. And what's really nice about this is BigQuery automatically creates new partitions for us every day. And it uses the ingestion time to determine which partition things go in. Now, it also creates a pseudo column called _partition time. So that's like an extra column in the table that we can use in our queries to determine which range or which sets of partitions we want to be scanning. Now, the partition time is a date-based timestamps, and we actually specified in the where clause, we can say where _partition time something, some condition. Excuse me. Now, there's also date timestamp partitioning. And this is similar to ingestion time in that it's based on a date or timestamp column. And each partition holds 1 day of data, but there's no need for a partition time column because we use one of the columns that already exists in the table. Now, there are a couple of special partitions that are created. There's the null or underscore null underscore partition, and that's where rows will go if they don't have a date in that particular column. Or if the value in the datetime column is outside the allowed range, then it'll go into this unpartitioned partition as well. And then the final type is called integer range partitioning. And this is just based on some type where we have an integer column. Now, it can't be a repeated field. It can't be an array of integers. It needs to be a scalar, so not a repeatable. Now, BigQuery has something called legacy SQL, which is an older SQL that was used with BigQuery originally, as opposed to standard SQL, which is what we use now. Integer range partition can't be used with that older legacy SQL, but I can't think of a reason why we wouldn't be using standard partitioning on a new data warehouse now. Excuse me, standard SQL on a new partition now. So this probably shouldn't be really much of an issue. Now, in other database management systems, you might have come across this idea of sharding. And sharding is the idea of using, say, a separate table for each partition. So, for example, have a separate table for each day. And you might name that table with some prefix like, sales orders, and then a particular date. And then you just have a bunch of these sales order tables. And then you use a union to query or scan multiple tables. And that is one way of doing it. But in BigQuery, partitioning is preferred over sharding because there's less metadata to maintain. So each of the tables in the sharding scenario have its own set of metadata. And there's also access control issues. So if there are fewer tables, then there are fewer times you need to basically check access controls and to determine, does a particular process or query or service that's trying to query the table actually have access to that particular table. So as a result, partitioning gives better performance than sharding. So definitely, in most cases, we want to prefer partitioning over sharding. Another thing we can do is set something called the require partitioning parameter. And what that means is that at a table, or even at a partition level, we can require that the partition column be used in the where clause. Now, this is useful if other people are querying your data and they might not know about partitioning and might not understand the implications of, say, doing a full table scan over a petabyte table and what that means in terms of performance and cost. So this is a way of basically at least putting guardrails on how much data somebody can pull back. Certainly, they could have a where clause that goes from the earliest date to the latest date, and you end up still partitioning scanning a lot of data. But at least the where clause gives you a mechanism to force people running queries to put some limits on the range of data that's being scanned. Now, I mentioned clustered tables earlier, and in a clustered table, the data is sorted based on values in one or more columns. And this can improve performance like with aggregate queries. So if you know like the sub-range where you want to say do a sum across some range and it's already clustered, it's pretty easy to find that. And it can also reduce the scanning when the cluster column is used in a where clause. So if you know, for example, if you're in a partition with values between 300 and 399 and you're looking for, say, 310 to 320, and if you know, as soon as you hit 321, you can stop scanning. You're never going to see another value in the range of 310 to 320 in that clustered table. So that's why clustered tables can further improve this idea of reducing the amount of data that's scanned. Now, partitions are like anything else in the universe. They're subject to entropy. So things start to get out of order. Especially as new data is ordered, it doesn't necessarily come in order. So as you ingest the data, you might need to reorder things. And that's okay because BigQuery automatically reclusters in the background, so we don't need to worry about that. This is just, again, another one of those like services that you might have had to think about earlier. Like if you used to use like materialized views and, when do we need to refresh and things like that. Or, how do you manage storage? You don't need to think about managing storage. You don't need to think about resorting your clustered partitions, because BigQuery just takes care of that for you. Now, the final sort of architectural piece that is different about BigQuery is the ability to use nested and repeated fields. Now, you can use nested and repeated fields in other databases, like Postgres will support nested structures like JSON and XML, and you can have arrays in Postgres. But it's not designed, like the storage structure isn't designed like Capacitor to be optimized to store that kind of data the way BigQuery is. So here, for example, is a screenshot of a part of the BigQuery console, and I'm looking at some data sets, and I've opened up here on the left kind of column a public data set called Bitcoin blockchain, and I've highlighted the transaction table. And if you look at the transaction table, you notice it has attributes like timestamp and transaction ID, and both of those, one is an integer, one is a string, and then it has something called inputs, and that's a record. So its data type is record, and its mode is repeatable. So the repeated simply means we can have an array of these things. So we can have an array of these inputs, and let's take a closer look at those inputs. So inputs to this Bitcoin transaction have things like script bytes and script string and a number of other things. I'm not familiar enough with Bitcoin transactions to really understand what these things are, but I can tell that this is, from a relational data modeling perspective, this screams, oh, I need to create a separate table and use a foreign key from transaction to this other table where I will have transaction inputs, and each of these will be its own row. But with BigQuery, we don't need to do that. We can actually store this data together with the transaction inputs with the transaction data. And because we can take advantage of Capacitor and its ability to store recorded and repeated fields in an optimal way. So this is why we don't need to denormalize, or one of the reasons we don't need to denormalize, or at least we don't pay a penalty for denormalizing. And in fact, it can be advantageous to denormalize because this is a more efficient way of storing this kind of data. And what I mean by that is, like when transaction and transaction detail or transaction inputs, it's like if you're using a particular transaction, you're almost certainly going to be using some of the data in the inputs, and you would have to go and do a join, but you don't have to do that. That data is relatively easily accessible. So that kind of covers the key points I wanted to make. So I just wanted to reemphasize, when we're working with Bigtable, we just are constantly thinking about how do I deal with scanning? I know the basic operation is scanning, so I can use partitioning to minimize the amount of scanning. I can use clustering within a partition to further reduce the amount of scanning. Now I can use joins, and that's perfectly fine to use joins, especially joining large tables and small tables. That's certainly fine, but it often helps to denormalize and use nested and repeated fields to avoid joining, especially when you're joining large tables, like two large tables. If you can find a way to denormalize and use nested and repeated fields instead, that's almost always a better option. So that wraps up my talk. So I will stop sharing.